Hello, so today we are talking about spring oscillations in Lab 4. To introduce, our problem that we are exploring is, are we able to accurately predict the motion of an object oscillating on a spring in multiple directions using a Python program? And the result of this is, yes, we are able to accurately predict the motion of an object oscillating on a spring using Python. To outline my report, I will first discuss the fundamental physics concept used and the energy changes in Python. I'll also discuss the initialization calculations, and then I will finish with the results and the what does it mean questions. The physics models that are relevant to this system are Newton's second law, Hooke's law, and the concept of the force of gravity. Newton's second law is useful because it allows us to determine the position of the block based on the net forces acting on the block. Hooke's law is needed because our spring is interacting with our system and providing a force on the system. Hooke's law allows us to determine the quantity of this force. Gravity is relevant because it is the other force that is acting on our system. And we could see all these different forces modeled here in our coding. Now, in order to use these physics concepts, we first need to consider some initialization calculations. So, one of the very important things is obviously the spring constant. So how do we determine this? Well, in order to do this, we need to figure out the period of oscillation and then compare that to this equation here, and then we can figure out the spring constant. And now we figured out this period of oscillation by using our tracker. And we can see that one period of oscillation is equivalent to this space here, so this time interval from here to here. And then so if we just go all the way to the very end right here, and then end up dividing this by 1, 2, 3, 4, 5, 6 times, then we'll get our period. And then so from here we can figure out the spring constant, and we also need to know the L naught, which is the original spring's length without being stretched, and then so we can calculate that at static equilibrium, and then we can see how all of this goes into our coding here. And then we also need to consider our time parameters. And so we had to consider these with the video and tracker to make sure that our frame rate matched what the actual frame rate was. And so this was at 10.5 frames per second. We were also asked to analyze the energy changes in our Python coding. And this is useful because it allows us to see how the different forces will actually influence the different potential energies and the kinetic energy of our system. We can see all of that here in our coding. And we can also see where we manipulated the coding to give us the blue, red, green, and yellow corresponding to the kinetic energy and the potential energies. Now, in order to see all of these energy changes in action, I will run the Python coding. So we can see here that we have the total energy, and that always equals 0, and we can also see the different potential energies, the gravitational and the spring potential energy, and then we can also see the kinetic energy in blue. Now I'll go ahead and run the program one more time. So now take a look at this window here. We can see that the blue ball is the Python, and then the red ball is the actual position of our block. So we can see there's a little discrepancy between the two, and the reason that this is so is because the frame rate in the actual video was much lower than what we had in the Python program. And so as we ran the Python program, this caused the red ball to sort of jump around. And despite this, the actual position between the two different balls, the red and the blue ball, were actually very similar. So the what does it mean questions. So is the energy principle satisfied? Yes, from this experiment the energy principle is satisfied. We can see this in the graph because the total energy change always equals 0. The kinetic energy change, the potential energy change cancel each other out. So we can see this here. You can see the yellow line is the total energy change, and that is always 0. And so therefore the energy principle is satisfied. Now compare the period of oscillation from the x position data and the y position data. So to do this, like I said before, we used the periods here, and then we changed, instead of y, we then used x as well. So the x position data, we determined that the period of oscillation was 1.646 seconds, and the y position data was 1.519 seconds. And these two periods of oscillations are evidently different, and if we apply these to the equation above, we can see that the two spring constants will also differ. And it turns out that the spring does not have the same stretching abilities in both the x and y directions. And that is why the oscillations periods are not the same, simply because the spring constant in the x and the y direction are different from each other. So to conclude the results of this experiment, basically we did not have many issues. Our model was easily able to predict the motion of our oscillating block, and the only thing I would like to point out is that the block can't keep oscillating forever. It's just simply not possible. Now our computer model did not take the transfer of energy to friction and drag into effect, so this is where our model would break down. We wouldn't be able to accurately predict the motion of the block unless we included things like this in our Python code.